NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will learn how to solve logarithmic expressions and equations using the change of base formula. We will build intuition, learn 2 key rules, and practice with clear examples. Big idea. When an equation involves logarithms with different bases, a fast strategy is to convert all logs to the same base. The change of base formula does exactly that. Rule 1. The general change of base formula. Log base I of b equals log base c of b divided by log base c of a. Here, a, b, and c are positive, with a not equal to 1 and c not equal to 1. A helpful special case. Log base I of b equals 1 over log base b of a. Let us practice with a few examples to make this concrete. Example 1. Convert log base 2 of 7 to base 10 and approximate its value. Using the change of base formula with base 10, we get log 10 of 7 divided by log 10 of 2. Numerically, this is approximately 0.845, 1 over 0.3010, which is about 2.807. A quick visual. Think of the ratio as how many times the log of 2 fits into the log of 7. The ratio is a bit less than 3, which matches our approximate value. Example 2. Solve log base 3 of x equals log base 9 of 27. We will convert the right-hand side to base 3. Log base 9 of 27 equals log base 3 of 27 divided by log base 3 of 9, which is 3 over 2. So we have log base 3 of x equals 3 halves, hence x equals 3 to the power 3 halves, which is 3 times the square root of 3. Example 3. Solve log base 5 of x equals log base 2 of 8. The right-hand side is simply 3, because 2 cubed is 8. Therefore, x equals 5 cubed, which is 125. Important cautions. The base of a logarithm must be positive and not equal to 1. The argument of a logarithm must be strictly positive. Always check these conditions when solving equations. First, the problem statement. Then, method 1, a reminder using the change of base formula. After that, we will confirm the result with a second method based on substitution. The key tool is the change of base formula. Apply it to both sides. Now cross-multiply. Replace log 4 with 2 times log 2 by the power rule. Multiply to get 2 times log 2 squared. Take square roots of both sides to split into 2 cases. Convert each case back to exponential form to obtain the 2 values of x. Now confirm with a second method. Let y be log base 2 of x. That means x equals 2 to the y. Also, log base x of 4 equals y, which means 4 equals x to the y. Substitute x equals 2 to the y into that equation. Use power of a power to simplify. Express 4 as 2 squared and equate exponents. Solve for y and then recover x. Both methods agree. We start by displaying the example, then we proceed step by step. Step 1. Introduce a common variable x and convert the first logarithm to exponential form. The rule says log base b of y equals x if and only if b to the x equals y. Apply it to log base 3 of a plus 1. Step 2. Convert the second logarithm the same way and then substitute a plus 1 with 3 to the x. We use the same conversion rule. First convert. Now rewrite a plus 8 as a plus 1 plus 7 and substitute 3 to the x. Step 3. Move the term 3 to the x to the left side to isolate the constant on the right. We subtract equal quantities from both sides. This yields the equation 4 to the x minus 3 to the x equals 7. Step 4. Solve the exponential equation by inspection of small integers. We try integer values for x. 4x equals 1, the left side is 1, which is not 7. 4x equals 2, the left side is 16 minus 9, which equals 7, so x equals 2 works. Step 5. Back substitute into 3 to the x equals a plus 1 to find a. Use back substitution. 3 to the 2 equals a plus 1, so a equals 8. Step 1. Domain of logarithm. The argument must be positive. Step 2. Apply the change of base to write every logarithm with base 2. Step 3. express the bases as powers of 2. Square root of 2 is 2 to the 1/2, and 1 over 2 is 2 to the power -1. Step 4. Use the power rule inside the denominators. Step 5. Since log base 2 of 2 equals 1, simplify each fraction. Step 6. Combine like terms. 2 plus 2 minus 1 equals 3. Step 7. Divide both sides by 3 to isolate the logarithm. Step 8. Convert the logarithmic equation to exponential form. Step 9. Evaluate 2 to the third power. Step 10. Check the domain and state the solution set. 8 is positive. Here is the equation. 3/2 times log base 1/4 of quantity x plus 2 squared minus 3 equals log base 1/4 of quantity 4 minus x cubed minus log base 4 of quantity x plus 6 cubed. Step 1. State the domain conditions for the logarithms. Each argument must be positive. Because the first argument is squared, it only forbids x equals -2, while the other two must be strictly positive. So, the domain is x not equal to -2, x less than 4, and x greater than -6. Next, rewrite base 1/4 as 4 to the power -1 on both logs with that base. Because the base is 4 to the -1, log base 4 to the -1 of a quantity equals negative log base 4 of that quantity. Apply that to both terms on the right and to the term on the left. Use the power rule. Log of a to the k equals k times log of a. Each exponent of 2 or 3 comes down and multiplies the logarithm, simplifying to this line. Now divide the entire equation by 3 to simplify the coefficients. Add log base 4 of x plus 2 to both sides, and replace the constant 1 with log base 4 of 4. That gives this exact line from the algorithm. Use the product rule. The sum of logs with the same base is the log of the product. Apply it to both sides. Because logarithm with the same base is 1 to 1, the equality of logs implies their arguments are equal. So we set the inside expressions equal. Now expand the right-hand side and simplify. Move all terms to one side to form a standard quadratic equation. Factor the quadratic as x plus 8 times x minus 2 equals 0. The solutions are x equals 2 and x equals -8. Finally, check the domain. We require x greater than -6, less than 4, and not equal to -2. That accepts x equals 2 and rejects x equals -8. The valid solution is x equals 2. Example. We will solve the logarithmic equation exactly following the steps shown on screen. The problem states log base of x minus log base a squared of x plus log base a to the 4th of x equals 3/4 with a greater than 0 and a not equal to 1. Step 1. Apply the change of base for powers in the base. The rule says log base b to the k of x equals 1 over k times log base b of x. Using this rule, we rewrite the two powered bases. Step 2. Combine like terms because all terms are multiples of log base a of x. Compute the coefficient. 1 minus 1/2 plus 1/4 equals 3/4. So 3/4 times log base a of x equals 3/4. Step 3. Divide both sides by 3/4 to isolate the logarithm. If c is not 0, then c times y equals c times z implies y equals z. Therefore, log base a of x equals 1. Step 4. Convert the logarithmic equation to exponential form. The rule is log base b of y equals z if, and only if y equals b to the z. Hence, x equals a to the first power. Step 5. Simplify a to the first power. Any non-zero base to the first power equals the base. So x equals a. Step 6. State the solution set and confirm the domain. Because it is greater than 0 and it is not 1, the solution is valid. The solution set is the singleton set curly brace a. In this example, we will solve a logarithmic equation step by step following a precise sequence of rules. The problem is log base 5 of x plus log base 7 of x equals log base 5 of x times log base 7 of x. Step 1. Apply the change of base formula. We convert each logarithm to base x using the identity log base b of a equals 1 over log base o of b. Substituting gives 1 over log base x of 5 plus 1 over log base x of 7 equals 1 over log base x of 5 times 1 over log base x of 7. Step 2. Add the fractions on the left using a common denominator. The common denominator is log base x of 5 times log base x of 7. So the left side becomes the sum in the numerator over that common denominator. Step 3. The denominators on both sides are equal and non-zero for valid bases, so we can cancel them. If a over c equals b over c, with c not zero, then a equals b. This yields log base x of 5 plus log base x of 7 equals 1. Step 4. Use the product rule for logarithms. Log base b of m plus log base b of n equals log base b of m times n. So we obtain log base x of 35 equals 1. Step 5. Convert to exponential form and solve for x. Log base b of a equals c if and only if b to the c equals a. Therefore x to the first power equals 35. So x equals 35. Important note about the domain. For log base b of a, we require b greater than 0, b not equal to 1, and a greater than 0. When we use the change of base to create the terms 1 over log base x of 5 and 1 over log base x of 7, we implicitly assumed x is not 1, otherwise those denominators would be undefined. However, if we plug x equals 1 into the original equation, log base 5 of 1 plus log base 7 of 1 equals 0 plus 0, which is 0, and the product on the right side is also 0. So x equals 1 does satisfy the original equation. Therefore, the complete solution set is x equals 1 and x equals 35. Example: we will solve the logarithmic equation exactly as shown in the reference steps. The equation is log base 2 of x plus log base 3 of x equals the product of log base 2 of x and log base 3 of x. Step 1. Apply the change of base formula to rewrite every logarithm using base x. Log base I of b equals 1 over log base b of a. This gives 1 over log base x of 2 plus 1 over log base x of 3 equals 1 over log base x of 2 times 1 over log base x of 3. Step 2. Add the fractions on the left using a common denominator. The common denominator is log base x of 2 times log base x of 3. Step 3. Clear the identical non-zero denominators on both sides. That yields log base x of 3 plus log base x of 2 equals 1. Step 4. Use the product rule for logarithms. The sum of logs with the same base equals the log of the product. So we have log base x of 3 times 2 equals 1. Step 5 in meaning. Convert from logarithmic to exponential form. Log base x of 6 equals 1 means x to the first power equals 6, or equivalently 6 equals x to the power 1. Step 6 in meaning. Solve for x. Since x to the first power is x, we get x equals 6. Example: we will solve the logarithmic equation exactly following the shown steps. The equation is log base of x plus log base square root of x squared plus log base cube root of x cubed equals 4. We assume it is greater than 0 and is not equal to 1. Step 1. Rewrite the radical bases using fractional exponents. Square root of a is a to the 1/2 and cube root of a is a to the 1/3. Step 2. Apply the change of base rule for powered bases and arguments. The rule is log base a to the k of b to the m equals m over k times log base of b. Apply that to the second and third terms. Step 3. Simplify the coefficients. 2 divided by 1/2 is 4, and 3 divided by 1/3 is 9. Step 4. Combine like terms. 1 plus 4 plus 9 equals 14. So 14 times log base of x equals 4. Step 5. Isolate the logarithm by dividing both sides by 14. Step 6. Convert the logarithmic equation to exponential form. Therefore, x equals a raised to the 4/14. Step 7. Simplify the exponent. 4/14 reduces to 2/7, so x equals a to the 2/7. Step 8. Write the answer in radical form if desired. 2/7 power equals the 7th root of a squared. Step 9. State the solution set. The solution set is the single value, the 7th root of a squared. Recap. We rewrote the radical bases with fractional exponents, Use the change of base rule to express every term as log base of x, combined like terms to get 14 times log base of x equals 4, and solve for x to obtain x equals a to the 2/7, which is the 7th root of a squared. Here is our example. We will convert everything to base 2, simplify, and then solve for x. Step 1. Apply the change of base formula to write every logarithm with base 2. The rule says log base b of a equals log base 2 of a divided by log base 2 of b. Now, apply it to the first two terms. Step 2. Evaluate the denominator logarithms. Log base 2 of 16 equals 4, and log base 2 of 4 equals 2. Step 3. Treat log base 2 of x like a single variable and combine coefficients. 1/4 plus 1/2 plus 1 equals 7/4. Step 4. Isolate the logarithm by multiplying both sides by 4/7. Step 5. Convert the logarithmic equation to its exponential form. Log base 2 of x equals 4 means x equals 2 to the 4th. Finally, check the domain. Each logarithm requires x to be positive. Our solution x equals 16 is positive. See, check the domain. Each logarithm requires x to be positive. Our solution x equals 16 is positive, so it is valid. State the solution set. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.